No more amplifiers. Sorry about that. What? I'll just make a couple of comments about common mode feedback circuits. I pretty much covered that on the last lecture. So we talked about a common mode feedback circuit, and the idea was the common mode feedback circuit takes the average of two voltages, the voltage that we want to set at some quiescent value, and it compares them to the desired value of the voltage, and then generates a feedback signal. It amplifies this difference and then generates a feedback signal, and that feedback signal goes to one of the places where we can inject a common mode voltage into the circuit. And depending on whether you go to the upper or the lower terminal will depend upon whether it's inverting or non-inverting input. We also talked about the common mode offset voltage, and that was the residual voltage that you have at the input biasing node to get the quiescent output to be where you want it to be at. We observed that we could look at a common mode half circuit, and there were several common mode gains. Each of the biasing points, each of the points on the axis symmetry was a different common mode input. So we can get common mode gains from those inputs. Of course, we talked about the common mode input that we provided to the signal path as well. Those common mode gains are entirely different. It makes a big difference when we're doing common mode feedback for establishing the correct operating point as to which one of those common mode gains we look at. So the common mode gain from the signal input is usually very small. It has almost no bearing on the common mode feedback path. The common mode gain from the biasing points are much larger, and they're what determines the characteristics of the common mode feedback loop. So here was the overall structure that we have then. I'm just showing it in single-ended form. The other half will be over here. And I don't show the averager here. So this is the average value of Vout1 and Vout2 right here that goes into this difference amplifier. And the averagers are usually very simple. The averagers are oftentimes two resistors. If you take two resistors and drive them on the two sides, the voltage between the two resistors is the average of the two voltages. So the averager circuits are usually real simple. Here, I don't see very many common mode feedback circuits published. And I'm not exactly sure the reason for that. Maybe one reason is we can get by with a small number of different common mode feedback circuits. So the circuit on the left is a common mode feedback circuit. Now this doesn't have the resistors in it. This common mode feedback circuit actually has two differential pairs, and your two outputs are here. And your average value, you can show the average value of these two signals appears on this current here, and that generates the common mode feedback signal. This is a switch capacitor common mode feedback circuit. And here what we do is we sample the voltages Vout1 and Vout2 on two capacitors, then put the capacitors in series, and the voltage in between is the average value of the two voltages. I'm not going to go through the analysis of this circuit here today because we will analyze switch capacitor circuits later, and we can see how that circuit works at that time. I should point out that you can use switch capacitor common mode feedback circuits even if you don't have a switch capacitor amplifier application. You can use a switch capacitor circuit to establish the Q point in the amplifier. And here's a modification of the original structure. I can add another bias current source, and I can double the common mode feedback gain by adding one more transistor M7 and one more bias and current source. Your author talks about the details on this circuit. So if you want to look at how this common mode feedback circuit works, I just refer you to the textbook for the course. Any questions about amplifiers? like to spend the period today talking about data converters. We'll spend several lectures talking about data converters. There are two types of data converters, ADCs and DACs. An ADC converts an analog signal to a digital output, and a DAC does the opposite. It converts a digital signal to analog output. The A to D converter is the most widely used mixed signal component. The DAC is often included in the feedback path of an ADC, although there are a lot of applications for DACs as standalone elements as well. The data converter fields will provide job opportunities for the foreseeable future. As technology advances, things that used to be working for building a good data converter no longer work. So we typically look at new solutions. Also, much like op-amps, we have data converter applications that vary wildly from one application to another. So the idea of putting a universal data converter into a system is something that's probably never going to be practical. We typically tailor our data converters to the particular requirements. When we start looking at the characteristics of a data converter, I think we'll see why that it's important to tailor the data converter to a particular application. Since they're so application dependent, we're going to have people designing data converters for a long time. So here's the basic structure of a DAC. I'm having problems with my PowerPoint. I cleaned the slides up on the PowerPoint version I had last night, on a different PC, and they show fine. The graphics are screwed up here. This is the DAC. This is supposed to be the input vector. So that square on top is supposed to be a caret. It indicates an input vector, n bits wide. There's always a reference on the DAC. And then the output is an analog representation of the input relative to the reference voltage of the DAC. Now, I haven't shown voltages here or currents here because data converters don't necessarily have to have voltage units or current units at the output. They can be different types of structures. Could be current, could be voltage, or it could be some other quantity. Although most of the time, the reference is voltage, but it doesn't have to be. Here's a structure with differential inputs. So the input can be, the output can be differential, and oftentimes if we have differential outputs, we'll have two references, an XREF plus and an XREF minus. The symbol that's used for a DAC is typically, as shown here on the right, and oftentimes we don't put in XREF on the symbol. It's understood that if you're using a DAC, there has to be a reference voltage someplace. Occasionally, the reference voltage is then generated internal to the DAC on a catalog part. So the consumer only has to put in an analog input voltage, and it will give a Boolean out. Designer has to only put in a Boolean input, and it will give an analog output that is proportional to the reference voltage and the Boolean input. The Boolean input is assumed to be n bits wide. We oftentimes will use B0 to denote the LSB and Bn minus 1 to denote the MSB. Most authors use this notation, but some will use different notation. Do you want to call the first bit 0, or do you want to call it bit 1? Do you want the MSB to be bit 1, or do you want the LSB to be bit 1? So the notation we will try to use in the course is B0 will be the LSB, and of course it will be represented on the right side of this Boolean bit. An ideal DAC is characterized at low frequencies by its static performance. We'll talk about that static performance next. So here's an ideal DAC. This happens to be a 3-bit DAC. And so we see that there are 8 different input codes, 000 through 111, and for each of the inputs, there's a corresponding analog output. I'm showing the reference voltage right here on this axis. A DAC really should be represented as a stem plot. A lot of times you'll see people use a plotting program and they'll connect these points together, but there really is no connection. A DAC is really represented as a stem plot. It gets tedious to represent the inputs in Boolean form. So oftentimes we will have a code, CK, corresponding to the Boolean input, the case Boolean input. So these are code representations of the corresponding binary input. So C0, code C0 corresponds to 000, and C7 corresponds to Boolean signal 111. On this ideal DAC, the biggest output is 7/8 of CREF, 7/8 of XREF. And notice I call that an ideal DAC. There are other ideal 3-bit DACs that differ from this one. We'll talk about what those differences are. So here, this is an ideal 3-bit DAC. Notice that the output doesn't go into the upper extreme. We could have another ideal DAC where at code 111, the output went to XREF, but at code 0, maybe it was 1/8 of XREF above 0. So there are different ways that we could to define an ideal DAC. If you have any ideal DAC, you should be able to put a straight line between the outputs of that DAC, irrespective of what the range is of that DAC. So all the points of this ideal DAC lie on a straight line, as well as any other ideal DAC. Now I should be careful. There are some DACs that don't have uniformly spaced outputs ideally. And those would be called companding DACs. So sometimes in the audio arena, you may intentionally have a DAC that has a nonlinear relationship between the Boolean input code and the output. But we're going to not be concerned about those types of DACs. Usually the number of bits of resolution is determined by using all possible codes for a given number of decimal digits. So consequently, the number of outputs of a DAC is typically a power of 2 to the n. I don't really know the reason for this. So if you have a DAC, an 8-bit DAC might have 256, will have 256 outputs. 7-bit DAC has 128 outputs. I don't know why you couldn't have a DAC with 100 outputs or 50 outputs. I can see some applications where a DAC with 100 outputs might be preferable. If you're trying to build a thermometer and want a digital output, and you want resolution of 1 degree centigrade, maybe you would prefer to have 100 outputs rather than 128 outputs. I conjecture the reason that we have the number of outputs being a factor of 2 is that if you have the number of outputs that's between bigger than 2 to the n minus 1 and less than 2 to the n, the hardware is about the same as if you have 2 to the n outputs. Okay? So when we were building DACs with discrete components, I think you wanted to get as much bang for the buck as you could. in integrated form, if you were to waste a few output levels, I don't see a big problem with that. Yes?
Could we maybe conject that it's dictated by what computers are capable of, and if register sizes go up by a factor of 2, it makes sense for our input to be able to match the register?
You still could use the same Boolean inputs, but you don't necessarily have to have your outputs have the same number of levels. You could throw away a few codes. There would be nothing wrong with that. Does that make sense? But almost all of the DACs today will have a number of levels that's a power of 2. So we can represent the output of a DAC then as XREF times, for this ideal DAC, as XREF times summation j goes from 1 to n of the Boolean signal b sub n minus j divided by 2 to the j. And you can see that gives you then the corresponding analog output for a given Boolean input. This representation is useful if you're doing simulations in MATLAB and so forth to represent what an ideal DAC looks like. If you look at the number of outputs, for n large, the number of outputs gets really big. In this example, I only have 3 bits, so I have 8 outputs. But if I had 16 bits, I'd have about 64,000 outputs. So there's a lot of outputs for a large n. If you look at the spacing between the outputs, the spacing between the outputs is almost always the reference voltage over 2 to the n, where n is the number of bits. So if there are 3 bits like we have here, then the spacing between the outputs is XREF, I can show it here, over 8. So we start out then with 0, and then XREF over 8, 2 XREF over 8, 3 XREF over 8. And by the time you get up to the 8th output, you're at 7 XREF over 8, and that's why the output doesn't go up to XREF. If we have a 1 volt reference, and n is 16, then I said there was about 64,000. It's actually 65,536 outputs. And the distance between 2 outputs is called the LSB. It's called the LSB at the output. And it's XREF over 2 to the n. And if you take 1 volt divided by 65,000, the LSB is 15.25 microvolts. So those are very, very, very small increments on the output of that DAC. Here's an alternate ideal 3-bit DAC. And this 3-bit DAC, again, has 8 outputs, but some of them are positive and some of them are negative. But what's important is the spacing between the outputs is XREF over 8 in this case. And what else is important is that you can put a straight line in between the points. Could these points move around? I've got these uniformly spaced on this axis. Could these points move around? Could C6 be here or here? Well, for
as long as the amplitude changes and it keeps the linear line in there, should be okay, right?
Yeah, it might appear that way here, but keep in mind this is a Boolean axis. So this is not defined between these points here. So by definition, if you plot it this way, these will be uniformly spaced because these are just Boolean codes. See, there is no Boolean code between 2 of the existing Boolean codes for a given bit resolution. Here are some applications of DACs. waveform generation, voltage generation, analog trim or calibration, industrial controls, feedback elements in ADCs. Could be used as a feedback element for common feedback circuit and op-amp as well. You can put a Boolean input in and use that to control that voltage on the biasing terminals. So how do we use it for waveform generation? So here's an example of a sawtooth generator. We start with a clock generator. And I'm showing an input called a period, but it just adjusts, that input is just going to determine the period of the clock generator. Could be a resistor, it could be a capacitor value, or it could be an external clock. And then we're going to go into an n-bit binary counter. And then we take the output of that n-bit binary counter, which should now be n bits wide, and we run that to a DAC. And so as that counter counts up, we keep turning on one more LSB, one more LSB, one more LSB all the time. And if that serves the input to the DAC, the output steps up. And when you overrange, it starts over again. So it gets up to 111, and it starts over at 000, and it should go up to 111 again. So this is a ramp generator, and this is what we might get for 3 bits. If n is larger, we get a waveform like this. If you zoom in to this region here and expand it, you still see these steps in here. But these steps can be so small that you hardly notice the presence of those steps in the output waveform. Okay. These types of this type of an approach is used in a lot of our high-end test equipment for generating our ramp waveforms. We just have a DAC, and we might put a filter on to smooth a little bit of that roughness off on the output of the DAC, but not very much. We probably don't care in many cases if there's little steps there, because the steps are really small. Here's a sine wave generator. Generating a square wave, generating a ramp and a sine wave at the same frequency is a little bit of a challenging task with analog components. But this works very well. So what we do here is we take the output of the binary counter and we run that into a ROM, or it could be a RAM that we program. And what it does is it converts the Boolean input that came from the sawtooth waveform into a different Boolean output that represents the sine wave value we would like at that point. And then we take that Boolean value and put it into the DAC, and we generate a sine wave that way. In fact, this becomes an arbitrary waveform generator, because in that RAM, you could put any waveform shape you wanted. Okay. If you have a large number of bits of resolution on your DAC, you get a high spectral purity waveform out of this waveform generator. We have some distortion of the waveform that's occurring, or I should say perturbation of the waveform that occurs due to both amplitude and time quantization. I can't put outputs infinitely fast. So I put an output here, then I gotta wait a little bit till I get the next output. So that's a time quantization effect. And I only have so many levels of resolution on my DAC. That's an amplitude quantization. Now notice on this output here, I have steps of different sizes. So right here, where the waveform is changing slowly, I'm getting a step of this size, maybe a small step. In the region here where the waveform is changing more rapidly, I get bigger steps. So I may actually jump codes here. When I'm trying to generate the sine wave, I might jump a whole bunch of codes where the sine wave slope is steep. And I may not jump any codes where the sine wave slope is very shallow. We oftentimes precede or follow with a buffer amplifier to smooth out these time domain and amplitude quantization effects. I can take the output of this waveform and run it into a low-pass filter, and that will pretty much take out these effects that we have here. Also, our DACs are usually not designed to drive a very heavy load. So the output buffer and filter will allow you to load down your output waveform without causing problems with screwing up the characteristics of the DAC. ADCs are kind of the opposite of DACs. They have an analog input, also a reference voltage, and a Boolean output. You can also have differential references. You can also have differential inputs. I didn't show it on the DACs. You can also have differential outputs on the DACs. So here's a situation where we have single-ended input and differential ref. Here we have differential inputs and differential refs. If you look at this structure here, the input range is from XREF plus to XREF minus. If you have differential inputs here, this one can be bigger than this one, or this one can be less than this one. So the input range is typically twice XREF plus minus XREF minus. In the positive going direction, it can be FREF plus minus XREF minus. In the negative going direction, it can be XREF plus minus XREF minus. So the total range is twice XREF plus minus XREF minus. It's most common when we're building integrated data converters, whether they be DACs or ADCs, to have differential inputs on the ADCs and differential outputs on the DACs. Here's a symbol we have for the ADCs. Again, the input is on the point of the triangle on the left. We'll try to follow the same notation. I use D's instead of B's here. So D0 is the LSB and D sub n minus 1 is the MSB. And much like a DAC, at low frequencies, an ADC is characterized by its static performance. So here is a plot of the transfer characteristics of an ideal 3-bit DAC, 3-bit ADC. Notice that the input is between 0 and this first point here. The output code is 0, 0, 0. Then we have a range of inputs where the output is code 0, 0, 1. And then adjacent to that, we'll have another range of inputs where the output code is 0, 1, 0, and so forth. The distance between two transitions on an ideal DAC is called the LSB. The distance between two transitions on an ideal ADC is called the LSB. If you look at the last transition, if the first transition occurs here, this will be typically 1 LSB. It could be something else, but if it's 1 LSB, then the last transition is going to occur at XREF minus 1 LSB. So this is much like what happened in the DAC. The inputs from XREF minus 1 LSB on up to as big as you want, ideally, will all be 111s. I put another vertical axis on here. Keep in mind that the output of an ADC is a Boolean signal. So the second axis here is the interpreted output. And the output of an ADC is dimensionless. The input of an ADC is dimensioned. It's current, it's voltage, it's something. It has some dimension quantity. Output's dimensionless. But the goal at the output is to have a dimensionless quantity that can be interpreted in terms of the dimensioned input quantity. So the second axis I put on here is what I call the interpreted axis. So code output code 0, dimensionless code, corresponds to 0 value of the dimension quantity. Code C1 at the output, that means code 0001, corresponds to the dimension quantity XLSB. Next code 2XLSB and so forth. Much like the DAC, we can look at how the Boolean output of the ADC relates to the input. Now, with the DAC, we had a simple equation that said how the analog output relates to Boolean input. We had a finite number of Boolean inputs. For an ADC, we have an infinite number, we have a continuum of analog inputs, but a finite number of outputs. So, ideally, the input signal would be equal to xref times this binarily weighted representation of the input. But since inputs exist between the transition points as well, there's going to be a little bit of difference between the interpreted value of the input, in digital form, and the actual input, and that difference I call the error epsilon. Epsilon is ideally small, and it's typically less than 1 LSD. So here's another representation of that same equation. We can think of a ADC as something that has bins. And each bin corresponds to a range of analog inputs that have the same digital output. If n is large, that is, we have a large number of bits of resolution, we have a large number of bins. So any analog input should drop into one of those bins, the bin corresponding to the Boolean output. The spacing between these transition points, and we oftentimes call these breakpoints or transition points, the spacing between the transition points is ideally xref over 2 to the n. Now I'm assuming here that we have a singulated input. We can modify this equation appropriately if we have a differential input. And as you can see, if xref is fixed and n gets large, the spacing between two transitions can get very small. Since I'm looking at ideal ADCs right now, ideal ADCs have an error. That's this error epsilon. So for an ideal ADC, this error is called a quantization error. Any ADC has a quantization error. It's the difference between the actual analog input and the interpreted value of that input. So these points where the transitions occur, I said, are called transition points or breakpoints. For an ideal n-bit ADC, there are 2 to the n minus 1 transition points. There are 2 to the n output levels. There are 2 to the n minus 1 transition points. Each of the transition points are separated by 1 LSB, which is xref over 2 to the n. For an ideal ADC, they're uniformly spaced. If you look at an actual ADC, you'll find those transition points differ a little bit from what you want. Likewise, for an ideal DAC, the output values will differ a little bit typically than for what you want them to be. I'm going to make what appears to be a simple definition. I'm going to define the transition point XTK to be the breakpoint where the transition in the code output to code CK occurs. So here I have a transition to code C1, so I call this XT1. Here I have a transition to code C2, so I'm going to call this XT2 and so forth. Pretty simple definition, right? The seemingly obvious ordering of the breakpoints becomes ambiguous, though, when more than one breakpoint may cause a transition to code CK. So in this case, if I want to go to code CK, there's only one transition point that corresponds to code CK. But if you have a non-ideal ADC, it could be the case that the non-ideality will result in a different transition point, also having an output that goes to code CK. So when we start considering non-ideal ADCs, characterizing those non-ideal ADCs may start to become a challenge because we can't even naturally order the transition points. So here's an ideal ADC and the corresponding output codes. We said, apologize for this PowerPoint issue. I don't know what to do about it. The quantization error is the difference between the input and the interpreted output. And if you look at the error, you can subtract the interpreted output from the input, and you'll have an error plot that looks like this. And so we say that the output, for example, in this region here, the output is 0. It's code 0, which corresponds to 0. But the input is changing. So here the input is 0, so there's no error. But here the input is some positive value. So if you take the output of 0 minus some positive value, you have a negative error. And that error will grow down until just before you get to this transition point. At this transition point, the input is XLSB, and the output is still code 0, so the error will go down to minus an LSB. Then a transition will occur, the error will jump back up to 0 and keep coming down like this. So these are quantization errors in an ADC. The magnitude of the quantization errors are bounded by an LSB for an ideal DAC, for an ideal ADC, excuse me. The magnitude of the quantization errors, at least between 0 and X rep, the magnitude of these right here is 1 LSB. Again, other ideal ADCs, the magnitude of the quantization errors will still be bounded by 1 LSB. Here's another ideal ADC. How does it differ from the previous one? I've done what? I've shifted the first transition point from 1 LSB to a half of an LSB. They're still uniformly spaced, 1 LSB apart, but I start the first one at a different point. Okay? Quantization error, same as what it was before. Now, so here's what the quantization errors look like. Again, the magnitude of quantization error is 1 LSB. But the maximum value of quantization error here is half an LSB. On the previous case, it was 1 LSB. You'll find in most applications, the performance of a DAC, an ADC that has this set of breakpoints and that has a previous set of breakpoints will be about the same. What we're really most concerned about is the peak-to-peak value of this quantization error. If that quantization error is offset a little bit, it doesn't affect the performance of most systems. There's a large number of different circuits that have been proposed to build data converters. What we find is that the different structures oftentimes have significantly different performance. However, the performance of almost all structures are identical if you use ideal components. So, much of data converter design involves identifying the problems associated with a given structure and figuring out ways to reduce these problems to an acceptable level. In fact, a data converter designer will spend almost all their time trying to find out what can go wrong in that structure, and then look at what you can do to fix that problem. It's critical that all problems that are significant be identified. Oftentimes there will be several different factors that cause a given structure to perform non-ideally. If there are 6 factors that cause a data converter structure to perform non-ideally, and they all result at about the same level of effect on the output, and you only take care of 5 of the 6, you probably still don't have a good structure. You've got to go in and find all of the structure, all of the non-ideal effects that will cause degradation of performance at a given level. Many of the problems are statistical in nature. They're usually associated with not being able to maintain close enough matching in our architectures. And not solving problems, and if you don't solve these problems, the result is a yield loss. The yield loss can be dramatic. You might build a 12-bit ADC, and it may be dependent upon matching of components. If you don't match them close enough, you might have a yield of way less than 1%. A minor change in the characteristics of your design might change the yield from 1% to 99%. Okay, so you have no choice but to look at the statistical aspects of your architecture. So the way I'm going to approach it in this course, I'm going to first spend a little bit of time looking at some different data converter architectures, and then we'll go into more detailed discussions about specific architectures and how you might make that architecture work. There's 2 general classes of data converters: Nyquist rate and oversample. In the Nyquist rate category, we have flash and charge redistribution and pipeline and 2-step and multi-step structures, interpolating, algorithmic, successive approximation, single slope and dual slope, subranging, folded, interleave, current steering, R-string, a whole bunch of different structures. In the oversampled category, we have discrete time and first order and higher order and continuous time, and so forth. So a lot of different structures in both the Nyquist and the oversampled category. In the Nyquist data converters, we get one output for each clock transition, whether it's an ADC or a DAC. For an oversampled data converter, we may have 10 or 100 or 1,000 samples that we combine in some way to get one output. We'll spend most of our time in this course talking about Nyquist rate structures, but we'll try to talk about what the characteristics are of the delta sigma structures as well. So I'll look at 2 structures and then we'll break. Here's a flash structure. On a flash structure, we have 2 to the n comparators, and we have 2 to the n resistors. We put reference voltages on top of the resistor string. That ideally sets up uniformly spaced voltages between 0 and Vref. Those serve as the minus input to the comparators. The input signal goes in the plus input to the comparators. The output is a thermometer code. The output will be zeros down to some point and then ones below that, depending on what the input is. We then go to a thermometer to binary decoder to get a binary output. So this is a basic flash architecture. Real simple, isn't it? If n is 16, however, it requires 64,000 or 65,000 comparators, which is not attractive. And here's a SAR ADC, successive approximation register. It only has one comparator, and it has a DAC. And what we do is we guess an input to the DAC, compare it with the input, and see what the output is. And if we guess often enough, we can see that comparator output change between 2 successive Boolean inputs. Then probably either of those Boolean inputs will be an acceptable output to that ADC. If we had to go through all combinations, we might have to test things if it was 16-bit ADC, we might have to have 65,000 tests. Oftentimes we'll do a binary search, however, so instead of having 65,000 comparisons, we could get by with 16 comparisons and converge to the right code. What we'll find is that for all ADCs, the conversion from the analog domain to digital domain is always done with a comparator. So building an ADC just depends upon how clever you can use one or more comparators to do the conversion from the analog domain to the digital domain. The Flight ADC used 2 to the n comparators. The SAR ADC uses 1 comparator. Are there any questions? I will post the exam on the website. There's one problems in color, and I didn't have them printed in black and white, in color, excuse me. So you may want to look at the color part on the website. Hopefully everything, there's different gray tones, so you can really separate the gray tones. And I guess that they're due at the end of the day on Friday.
What is the end of the day? What time is that?
5 o'clock?
Oh, we're done.
Pardon? Where at?
Yeah, we're
My office? I request this be individual effort. My goal is to have this be a learning experience. I'm willing to answer questions you may have, or it depends on the problems. I would like to have everybody do perfect work on it. So hopefully that will happen.
You're only allowed to ask or
Prefer to have, you're welcome to talk to Ben if you want to as well. It says on your memo, but Ben is available to catch you.
I know, but like if you had looked at the first 2 problems on the Olympic side, so now I feel a little bit better.
The answer's not there.
Yeah, but I mean, you can still spend time figuring out how to do it. Yeah. No.
Wait, how else? Unbelievable, right? What? 12 hours of sleep? Yes.